Bismillahirrahmanirrahim. Assalamu alaikum dear students, I hope you are fine. So in today's lecture we will consider about the bonding and hybridization. So the key concepts which we'll consider about in today's lecture will be the bond, what's a coordinate covalent bond, what's hybridization, and lastly we'll consider about the delocalized and localized bonding. Alright, so what's a bond? In the last lecture we saw that bond is just a force of attraction that holds the two atoms together. Alright, so this bond is just a force of attraction. And then in the last lecture we also said that the ionic bond is just a bond that is formed by transfer of electron from one atom to another, while covalent bond is a bond that is formed by mutual sharing of electrons. Alright, so if electrons are shared between the two atoms, then in that case will form a covalent bond, while if one atom loses electron and other gains the electron lost by the first atom, then the bond is called the ionic bond. We also saw that the ionic bond is always formed when one of the atom is a metal and other is a non-metal, while the covalent bond is always formed between non-metals because neither of the atoms wants to lose electron or gain electron because that's not energetically feasible. Also we saw that why a bond is formed. So a bond is formed only in order to gain the stability. Why to gain stability? Because when an atom forms bond, it does so in order to complete the outermost shell. So a complete outermost shell will result in decreasing potential energy, and decreasing potential energy will result in gain in stability. So the atoms tend to become stable. That's why they form bond. So they can form ionic bond, they can form coordinate bond, and there's a third type of bond which we'll study here, that will be coordinate covalent bond. So we'll here study the coordinate covalent bond. So covalent bond is a bond in which both electrons are donated or shared between the two atoms. While in a coordinate covalent bond, both electrons are donated by one of the bonded atoms. Right? So coordinate covalent bond is a special type of covalent bond. Right? So if you have to define a coordinate covalent bond, just read carefully. So a coordinate covalent bond is basically a covalent bond in which both of the electrons are donated by one of the bonded atoms. Right? So it's not mutual sharing. So the covalent bond is defined as an atom in which the electrons are shared mutually between the two atoms. It means both atoms donate one electron each, while in case of coordinate covalent bond, both of the electrons are donated by one atom. They are not shared mutually, but once they are donated by one atom, then they are shared. Right? This is sharing, but that's not mutual sharing, because what happens that an atom donates 2 electrons, and these 2 electrons are there shared between the atoms. So coordinate covalent bond is actually a special form of a covalent bond. So in a coordinate covalent bond, the atom which donates the electron pair is called the donor. It's also known as the Lewis base. And the atom which accepts the electron pair is known as acceptor, or also known as the Lewis acid. So if you just keep in mind the Lewis concept of acids and bases, we'd say that any species that can donate an electron pair is called a Lewis base, while any species that can accept the electron pair is called Lewis acid. So coordinate covalent bond in which the atom which is donating the electron pair, that's the donor, also known as Lewis base, while the atom which is accepting the electron pair is called the Lewis acid or the acceptor. And the coordinate covalent bond is represented by an arrow that points from donor to an acceptor. So for example, say here we have water molecule. In this water molecule, this oxygen is donating an electron pair to this hydrogen, which is actually the proton acceptor. Right? So this hydrogen, that's positively charged, it has no electrons. Right? So oxygen, what it happens that oxygen donates the 2 electrons of its to this hydrogen. So oxygen is electron donor. So this oxygen is acting as a Lewis base, while this hydrogen is electron pair acceptor. So that's actually acting as Lewis acid, and coordinate covalent bond is represented by an arrow that's pointing from the donor to the acceptor. Right? So ionic bond. In ionic bond, so there's no use of any arrow or dash. Covalent bond is represented by a dash. So if there's a single covalent bond, you use 1 dash. If 2 electron pairs are shared, you use 2 dash. And if 3 electron pairs are shared, then we use 3 dash. But in case of coordinate covalent bond, you can say there is a single dash between oxygen and hydrogen. That means that's a single covalent bond. Again, a single dash between oxygen and hydrogen. There's also a single covalent bond, but there's an arrow between oxygen and hydrogen. It means this bond is coordinate covalent bond because this is donor and that's acceptor. Also, the coordinate covalent bonds are normally represented in these square brackets, and there we get a positive charge here. It means that this whole of the molecule is positively charged because one atom has donated electronic density, and because it has donated electronic density, so it has become partial positive. Then it's got a positive charge on itself. So here we have full positive charge inside. Alright, so this is the coordinate covalent bond. So let's consider that coordinate covalent bond is formed which type of atoms. So in order to form a coordinate covalent bond, it is necessary to have an atom that has the ability to give an electron pair. Right? You must have an atom that can donate an electron pair. Right? So who can donate an electron pair? Only those atoms can donate an electron pair which have lone pairs of electrons. Right? So we must have one atom that has lone pair of electrons. Right? So which atoms have lone pair of electrons? So if you want to see in the periodic table which elements have lone pair of electrons which can be donated, then you have to see group number 5, group number 6 and group number 7 of the periodic table. So group number 5, this is the nitrogen family. So nitrogen family has one electron, one lone pair with it. So this nitrogen can donate one electron. So nitrogen can form a coordinate covalent bond. Similarly, group number 6, this is the oxygen family. So it has two lone pairs. So both of these lone pairs can be donated. So it has two lone pairs. It can also act as Lewis acid. So here we have group number 7. It has 3 lone pair of electrons. So group number 7, that are the halogens, they can also act as donors of electron pair. Right? So group number 5, group number 6 and group number 7 members. So the members of these groups can act as donors in coordinate covalent bond. Now we have the acceptor. So there must be an atom which must be deficient, and it should be deficient enough to accept an electron pair. Right? So what we have that in order to form a coordinate covalent bond, we must have a donor. So we know the donor must be from group number 5, group number 6, group number 7, and the acceptor must be electronically deficient. So in order to have an acceptor atom, we must have elements for group number 3. Right? So group number 3 elements, they are the members of boron family. So boron family is known as electronically deficient elements. Right? So why they're electronically deficient? Because they cannot complete their outermost shell. So just see the electronic configuration of the boron family. So they have 3 electrons in their outermost shell. Right? So they cannot lose 3 electrons because it's very hard to lose 3 electrons. And they cannot gain 5 electrons to complete the 8 electrons, and if they share electrons, they can only share 3 electrons. Right? So after sharing, they will get a total of 6 electrons, but they have to complete the outermost shell with 8 electrons, so they still have 2 electrons missing. Right? So group number 3 elements, since they cannot complete the outermost shell, therefore they are considered as electron deficient elements. Similarly, we can have a proton. So proton can also accept an electron because proton has 0 electron in its outermost shell. So proton is actually a hydrogen with a positive charge. Right? So it needs 2 electrons to complete the outermost shell. Right? Similarly, group number 3, they also require 2 electrons to complete the outermost shell, otherwise they will not be able to complete the outermost shell. So here we have the situation. We can say that covalent bond, the coordinate covalent bond must be formed between members of group number 3 and members of group number 5, 6 and 7. So whenever you have a member from group number 3, so we have made a generalization that whenever we have a proton or we have members of group number 3 which are electron deficient elements, then we always form a coordinate covalent bond when the donors from group number 5 and 6 and 7 are available. Right? So that's all about the bonding section. So now let's consider another concept which is important in organic chemistry, and this concept is hybridization. So what do we mean by hybridization? So hybridization is a concept in which we assume that we mix different atomic orbitals. So each of these atomic orbitals have different energies, different shapes, etc. And these different atomic orbitals, when mixed, they result in formation of new hybrid orbitals. And what what happens that all of these new orbitals, these new hybrid orbitals, have the same energies, they have same shapes, etc. Right? So what we did, we mixed different atomic orbitals with different energies, different shapes, different bond angles, and we get new hybrid orbitals. And all of these new hybrid orbitals have same energies, same shape, etc. So one thing is important, that if we mix two atomic orbitals, we get two new hybrid orbitals. The number of hybrid orbitals obtained after mixing of the atomic orbitals will be the same. Right. For example, we see that why we are in need for the hybridization, because in case of organic chemistry, hybridization is very important because it explains the tetravalency of the carbon. So according to valence bond theory, the valence bond theory states that a number of covalent bond formed by an atom is always equal to the number of electrons pair, to the number of unpaired electrons that are available in the valence shell. So in case of carbon, if we do the electronic configuration of carbon, right, so with two unpaired electrons in the outermost shell, the carbon is expected only to form two bonds. However, we know that carbon is tetravalent. Right, so this valence bond theory cannot explain the tetravalency of this carbon. So on this basis, we only assume that carbon can form two bonds only. However, this is not the case. So what we say that suppose that we say that in the excited state, one of the electrons from 2s is shifted to 2p. So here we have 4 electrons, and the valence shell now it can form 4 bonds. But if you critically see that these 4 bonds, if formed, they will be different, because one bond will be formed by the overlap with 2s orbital, while 3 bonds will be formed by overlap with 2p orbitals. So all of these bonds will be different. So this bond will be formed by overlap of 2s orbital, and these 3 bonds will be formed by 2p orbital. Also, if you know about the basic chemistry, you know that these 2p orbitals, they're directional. So all of these are at 90 degree, while this orbital of s is spherical. So you will have all 4 bonds of carbon which will be different. Right, the bond which will be formed by overlap of this 2s, that will be more spherical. This will be at 90 degrees, this will also be 90 degrees, this will be also 90 degrees. So I can explain the tetravalency of carbon when all of the bonds are exactly same and the angle is also same, which is equal to 109.5. So in order to explain this experimental evidence, the carbon has all of the bonds which are identical and they are at angle of 109.5, then we use the concept of hybridization. So we say that firstly, the carbon that will go in the excited state. So here we have carbon excited state, and after being converted into excited state, all of these orbitals, this s and 3p, these sp3, these 4 orbitals will mix together and they will form 4 orbitals which will be new. Alright, so these orbitals are hybrid orbitals, and each of these orbitals is known as sp3 orbital. You can say all of these orbitals are identical. Alright, so it happens that the bond formation by overlap of anything with these orbitals, so the bonds will be exactly identical, same in their shape, in their energy, in their bond angle, etc. So let's check the example of here. So here we have this methane. So carbon uses its sp3 hybridization. So these are the 4 sp3 hybrid orbitals, which are shown in like gray color from here. Right, so you can say that all of these orbitals, they are of exact same length, and the bond angle of orbitals is 109.5 between each of these orbitals. So this is angle 109.5, this is 109.5, this is 109.5. Well, they're exactly the same. So it happens that if you have to form the methane, then this hydrogen will form a covalent bond by overlap with this sp3 orbital. So there will be sp3s overlap. So here we have got a single bond between carbon and hydrogen. So again we have an sp3s overlap of this carbon and hydrogen, again sp3s overlap is carbon and hydrogen, and another sp3s overlap between carbon and hydrogen. In that case we can form methane. So you say that in methane, so we have explained the tetravalency of the carbon. Also we have explained why all of these bonds are exactly same. If you don't use this concept of hybridization, we cannot explain why all of these bond lengths are equal and why all of these bonds are of same length. Right, so we can have a summary that whenever sp3 hybridization occurs, then a bond carbon has 4 bonds attached to it. Right, whenever you see a carbon with 4 bonds, always remember that it has sp3 hybridization. Further, the sp3 orbital has 25% s and 75% p character. It means that this sp3 hybrid orbital resembles more like a p, right? So it's more dumbbell shaped, and it has less s character. The s character is more spherical, right? So sp3 orbital tend to be longer because it has more double shaped character. So if a bond has greater s character, it's more spherical. So if a bond is more spherical, then it's more shorter. And if a bond is more resembling like a p, then it's longer. So sp3 orbital, since sp3 hybrid orbitals have more of a p character, therefore these orbitals tend to be elongated. They are much longer. So the bond formed by sp3 hybrid orbital overlap, this bond tends to be long, right? And the bond angle between all of these four sp3 orbitals is 109.5. So some also state 109.25 or 28. So it doesn't matter. The important thing is that it should be 109 point something, right? So each of the sp3 orbital is involved in sigma bond formation, right? So it's a sigma bond. A sigma bond is a bond that's formed by head-on overlap, right? So let's see about that. So there we have sp3 orbitals overlapping, and they overlap by head-on head, right? So they overlap linearly. So when they overlap like this way, right, so you can say that the electronic density is symmetrically distributed between these two nuclei. So this red dot means the nucleus. The electronic density is existing between these two nucleus. So this bond is formed by head-on overlap. This bond is known as sigma bond, right? So sp3 orbitals overlap will always result in formation of a sigma bond. So next we see the sp2 hybridization. So in sp2 hybridization, what happens that again we have a carbon and it's in excited state. So here we have these orbitals in which each of the orbital has one electron each, right? What happens then when we have to carry out the sp2 hybridization? So one of the p orbitals does not participate in hybridization, so we mix one s and two of the p orbitals. So here we are considering this s and these two p orbitals, while this v orbital, this is not participating in hybridization. So you can see that when orbitals hybridize or when orbitals mix, so we have three orbitals sp2. These are of lower energy, while the orbital that has not participated in hybridization, that has slightly higher energy, right? This pv orbital is said to be unhybridized. This is not hybridized orbital, while these are sp2 hybridized orbitals. So we mix three orbitals and we get three orbitals. So since they are formed by mixing of one s and two p's, therefore these three orbitals are known as sp2 hybrid orbitals, right? So this is a hybrid orbital. What happens that when we get a hybrid orbital like that, so one of the sp2 hybrid orbital forms a linear bond. So this is a linear bond. So this linear bond between this carbon and this carbon is formed by the linear overlap between sp2 and sp2 hybrid orbital. So this bond, since it's formed by linear overlap, that's called a sigma bond, right? Similarly, these two orbitals, these are also sp2 orbitals, which are shown by the orange line. So they are linearly overlapping with hydrogen space. So here is a hydrogen and here is also hydrogen. Similarly, here and here we have hydrogen, right? So these orange lines, these are indicating the hybrid orbitals. So you can see that hybrid orbitals are lying in single plane. The bond angle between the hybrid orbitals is 120 in case of this sp2 hybridization. Now these greenish orbitals here, these are the orbital that was not participating in the hybridization. So just go for back. So here you can see this orbital, this 2pz orbital, which was not participating in hybridization. So this is that unhybrid pz orbital, right? So this is pz orbital of one carbon, this is also pz orbital of other carbon. So these two orbitals, they are parallel to each other and they overlap parallelly. So this is parallel overlap. So when they do the parallel overlap, what's formed is called a pi bond. So any bond that's formed by parallel overlap is called a pi bond. So in case of pi bonds, electronic density is available above and below the plane. It's not between the two nuclei. So sigma bond has electronic density that is present between the two nuclei, while pi bond has electronic density that is available above and below the plane, above and below the nuclei. It's not between the nuclei. So since pi bond is formed by parallel overlap, so this pi bond is a weaker bond, while sigma bond is a stronger bond, right? So because of this presence of a pi bond, so the free rotation between carbon-carbon bond cannot occur, right? So whenever there's a pi bond, always remember there will be no free rotation between carbon-carbon bond. And furthermore, always remember that a double bond, that is pi bond, cannot be formed by hybrid orbitals. A pi bond is always formed between unhybrid orbitals. It cannot be formed by the hybrid orbitals, always formed by the unhybrid orbitals. So let's consider. So we have bonding in ethene, right? So here we have these hybrid orbitals. So these are hybrid orbital, while that orbital that are perpendicular, this is the unhybrid orbital, right? Similar, this is an unhybrid orbital. So this is the sp2 overlap, the resulting in formation of a linear bond, a head-on overlap, and that's a sigma bond, and the sigma bond is present between the two nuclei, right? And these are two sp2 orbitals, and these sp2 orbitals are overlapping linearly with hydrogen, so again they're forming a sigma bond and similarly sigma bond. So this is the unhybrid p orbital, which I was referring before. So this unhybrid or pure p orbital, this overlaps parallelly and will form a pi bond. So just say that this pi bond, the electronic density is available above and below the two atomic nuclei, where the sigma bond is present between the two nuclei, right? So sigma bond is always stronger than a pi bond. Right, so again we have summary for sp2 hybridization, right? So hybridization, sp2 hybridization will occur when a carbon has 3 attached groups. When you see the carbon has 3 bonds, then always remember that it means that should be sp2 hybridization, right? So in sp2 hybridization, so we have 33% S character and 67% P character. So here you can see the S character has increased from 25 to 33%. Right? It means that this has some spherical character. So since there's a spherical character, it means more overlap and the bond should be stronger. So a double bond is stronger than a sigma bond. Right? So sp2 hybrid orbitals, the bonds that are formed by sp2 hybrid orbitals are shorter than the bonds that are formed by sp3 hybrid orbitals. Right? So always remember that when a bond is formed by sp2 hybrid orbitals, that should be shorter and more stronger than a bond that's formed by sp3 hybrid orbitals. The bond angle between these 3 sp2 orbitals will be 120 degrees, and each of the sp2 orbitals is involved in sigma bond, while a pi bond is formed by the unhybrid p orbital, right? And the double bond that's formed in sp2 hybridization has a sigma bond and a pi bond, right? So one of the bond is sigma, another bond is pi in case of sp2 hybridization. So let's consider about sp hybridization, how it occurs. So again we will consider firstly we have to explain the tetravalency. So one of the electrons from 2s will jump to 2p. So we have 4 electrons, 4 unpaired electrons in these orbitals. So now what happens that only 2 orbitals will mix. Right, so these 2 orbitals, they are involved in mixing. So 1s and 1p all mix together, so we'll form 2 hybrid orbitals. So they're called sp orbitals. Right, so these are sp hybrid orbital, while these 2 remain unhybridized orbitals, right? So in case of sp hybridization, we mix 1s and 1p and we get 2 orbitals. No, both of these are known as sp hybrid orbitals, and we have 2 unhybridized p orbitals here. Right, so here we have the bonding. So we have considered the bonding of acetylene as an example of sp hybridization. So just consider that in sp hybridization we have 2 hybrid orbitals. So one is this one and one is that one. So similarly, one is a carbon, so it has also hybrid orbital. So both of these sp orbitals, they will overlap linearly, and because of linear overlap will form a sigma bond. Right, so again these sp orbitals will overlap with hydrogen from sp orbital. So again that's a sigma bond here, right? So always remember that hybrid orbitals always form sigma bond. So there's again a sigma bond here, right? What remains are the 2 p orbitals that didn't participate in bonding. First that's a px orbital shaded in red, and here that's also px orbital shaded in red. So both of these are parallel to each other, so they will overlap if parallel and form a pi bond. Similarly, this is py orbital, so this is also py orbital, and both of these will also parallel overlap to form a pi bond. So in case of acetylene, right? So in case of acetylene, so we have a sigma bond and 2 pi bonds. So there is a triple bond here, right? So the triple bond, so the triple bond has a sigma bond and 2 pi bonds. So always remember that hybrid orbitals always form a sigma bond, while the unhybrid orbitals always form the pi bond. So in case of acetylene, so we have what? A sigma bond and 2 pi bonds. So we're just left. Let's have a summary. So sp hybridization occurs when a carbon has 2 bonds, or when a carbon has 2 groups attached to it. So just see example. So in that case, the carbon has 2 groups attached to it. So one group is that carbon and one group is the hydrogen. Right? So whenever carbon has 2 groups attached, always remember hybridization should be sp. And whenever the groups are 3, then hybridization will be sp2. And if we have 4 groups attached, then hybridization is sp3. Right? So in case of sp hybridization, we have 2 groups attached. So carbon has sp hybridization, and the sp hybridization has 50% S and 50% P. So you can see that the S character has increased further. So what you assume that because of increased S characters, there will be more spherical character, and since the spherical character has increased, so the bond will be shorter because of greater overlap. Right? So because of increased S character, there will be greater spherical character, and because of increased spherical character, the bond length will be shorter. So you can assume that bond formed by sp hybridization are shorter than the bond formed by sp2 hybridization, and the bonds that are formed by sp2 hybrid orbitals are. Alright, so due to increased S character, so there will be more spherical nature. Because of more spherical nature, there will be greater overlap, and because of the greater overlap, the bond will be much shorter. So you can assume that bond formed by sp is the smallest, the bond formed by sp2 is intermediate, and the bond that's formed by sp3 hybrid orbitals overlap will be the longest one. Right? Further, the bond angle between these two sp hybrid orbitals is 180 degree to each other. So these two orbitals at maximum degree of angle of 180 degree to each other, and whenever there's sp hybridization, we always get 1 sigma and 2 pi bonds. So we have a triple bond in case of sp hybridization. So we have seen about the bonding. We have seen about ionic bonds as formed by transfer of 1 electron from one atom to another. We saw the covalent bond, in which there was mutual sharing of electrons, and then we saw the coordinate covalent bond. So in case of coordinate covalent bond, so that's a bond in which one of the 2 atoms donate electrons, donate the electronic density, or donate the 2 pair of electrons, 2 electrons to the atom. So here we have the concept of donor atoms and acceptor atoms. Then we saw the concept of hybridization. So in case of hybridization, what's important, why hybridization is important, because if we don't use the concept of hybridization, we cannot explain the tetravalency of carbon. Secondly, we also cannot explain why all of the bonds formed by carbon are exactly the same. So in case of hybridization, we studied about sp3 hybridization, we studied about the sp2 hybridization, and we studied about sp hybridization, right? So now we are considering the bonds that are formed. So let's just for review into that. When the overlap between orbitals is end to end or head to head, we always get a sigma bond, right? And in case of a double bond, right, in case of double bond, we have 2 bonds, one is sigma and one is pi. So the sigma bond that's formed end to end overlap, while pi bond is formed by side to side overlap, right? Well, in case of triple bond, so in case of triple bond, we have a sigma bond which is formed by end to end overlap, and 2 pi bonds which are formed by side to side overlap. So you have to answer one of the questions, which is a short question for you, that how are the 2 pi orbitals in the triple bond oriented? Alright, so are they oriented in the same plane, or are they oriented parallel to the plane? So what is the way the 2 pi bonds in a triple bond oriented, and what's the angle between these 2 pi bonds? You have to answer that question. So let's consider another concept that's very important, basic concept, and this concept is about localized and delocalized bonding. So what is localized chemical bond? Let's consider that, for briefly I should mention that, you know, the bonding which we'll be referring will always be covalent bonding, so we'll not consider the ionic bond or coordinate covalent bonds. In organic chemistry, since we purely deal with the covalent bonds, so the bonding which will be referred to will be covalent bond only. So this concept of localized and delocalized bonding is only applicable for covalent bond. So let's consider what do we mean by localized chemical bond. So localized bond is basically a covalent bond, and it's a covalent bond in which the electronic density remains fixed between two atoms. Alright, so any covalent bond, it can be sigma bond or it can be pi bond, in which the electronic density remains delocalized. If electronic density remains fixed between two atoms, then such a covalent bond is called a localized chemical bond, and such type of bonding is called localized chemical bonding. Right, so just see that here we have two atoms and the electronic density you can see. So this pink color, that's indicating the electronic density. So this electronic density is fixed between these two atoms. It's not shared by any third atom. Right, so if the electronic density remains fixed between two atoms, then in that case such bonding is known as localized chemical bonding, right? So it's not necessary that the localized chemical bond will always be sigma bond. Can be also sigma bond, it can be it can be a pi bond, but the necessary condition is that the electronic density should be fixed between only the two bonded atoms. So let's consider the other concept of delocalized bonding. Right, so what are delocalized bonds? These are chemical bonds in which the electronic density is not associated between only two atoms, but the electrons are part of more than two atoms. Right, so if the electronic density, in short, we can say that if the electronic density is not fixed between two atoms but is spreading on more than two atoms, then such type of bond is called a delocalized bond, and such type of bonding is known as delocalized bonding. So just see that how we define that. So delocalized chemical bonds are the chemical bonds that are not associated with only two bonded atoms, but these are the electrons which are associated with several bonds and other chemical bonds as well. We call the electrons in these bonds as delocalized electrons, right? And the bonding is known as delocalized bonding. So what type of system show delocalized bonding? So let's see that which type of system will show the delocalized bonding. So whenever the delocalization occurs, it's always occur in a pi conjugated system. Alright, so it's a conjugated system. The conjugated pi system or simple conjugated system is a system in which there is alternate double and single bonds. So whenever you have a double bond, then a single bond, then a double bond, and then a single bond, etc., then such a system is known as a conjugated pi system or simple conjugated system. Right? For example, you may just take the example of benzene, for example. So benzene has 3 sigma bonds and 3 double bonds, and they are such that one double bond is followed by a single bond, then a double bond, then a single bond. So whenever there is alternation in double or single bonds, then system is said to be conjugated, and whenever the system is conjugated, the bonding is called the delocalized bonding. Right, so that's what we mean by delocalized bonding. So localized bond is a covalent bond in which the electron remains fixed between two atoms. However, if you have a system in which the electrons don't remain fixed between two atoms but they are spreading on more than two atoms, then such a system is known as delocalized bonding, and the system is said to be delocalized. Right, always remember that delocalization always occur in conjugated pi system. Right, so just you can see the benzene ring, right? So here this ring inside this benzene structure, so this ring is indicating that electrons are not fixed between these two atoms or these two atoms, but they are part of all of these atoms. Right, so this is indicating the delocalized electrons, and this is the delocalized bonding. Right, so delocalized bonding always exists when a system is conjugated. So here we have few structures, and this is your assignment. So you have number 1 to indicate the type of hybridization in each carbon. So this is a carbon, you have to tell what is the type of hybridization of this carbon, this carbon, this carbon, this carbon, etc. Right, so you have to mention the type of hybridization of each type of carbons, Second, you have to indicate that in which of these compounds we have delocalized bonding. Right, so these are the two questions you have to answer for these structures. So you have to mention number one, the type of hybridization in each of the carbon, and also indicate that which of the following compounds will show the delocalization of electrons, so which will show the delocalized bonding. Right, so that's all for today. And in case if you're looking forward to recommended books, so these are the two recommended books for this course. This is Textbook of Organic Chemistry by M. Yunus, and this will be Organic Chemistry Structure and Function by Peter O'Hart and Neil Shaw. Thanks for your patience.